Well, probably the biggest mystery in modern physics, wouldn't you say?
Oh, absolutely. The massive clash between Einstein's general relativity
Our theory for the huge stuff planets, stars, galaxies.
and quantum mechanics, which deals with the incredibly tiny atoms, electrons, all that.
And they're both amazingly accurate, right, in their own domains.
Phenomenally so.
Yeah.
But fundamentally, they just don't agree on how the universe works at the deepest level.
Yeah, things like space-time. Quantum mechanics treats it as fixed, like a stage.
But GR tells us space-time is dynamic, it bends, it warps, it's part of the show.
Exactly. And bridging that gap, that incompatibility, that's the huge quest, isn't it? The search for a unified theory, a theory of everything.
It's the holy grail, really.
So our mission today is to explore something related. How does the world we experience, the solid classical world, actually emerge from that weird, fuzzy quantum reality underneath? We're going to look at two really fascinating ideas from the sources you sent over. First, this concept of a de Broglie wavelength for, well, everything.
Even baseballs, yeah?
And second, string theory, the main contender right now for maybe unifying all of physics.
Right. We'll explore how matter can act like a wave, why, your car doesn't diffract like light does.
Huh. Thankfully.
And how these tiny vibrating strings might be the ultimate building blocks, maybe even explaining quantum rules in space-time itself.
So it's kind of a journey down through the layers of physical laws. Let's get into it. Okay, first stop. These hidden waves of matter. This idea came from Louis de Broglie, right? Back in the 1920s.
That's right. It followed on from Planck and Einstein, showing light could act like a particle, a photon.
Which was weird enough, light being a particle.
Totally. So de Broglie, in 1924, he thought, well, what about symmetry? If waves can be particles, maybe particles can be waves.
Like electrons, protons, that sort of thing?
Exactly. He proposed that matter, fundamentally, has a wave-like nature associated with it.
And this wasn't just an idea. It got proven pretty quickly, didn't it?
Yeah, just 3 years later, 1927, Davison and Germer in the U.S. and George Paget Thomson in the U.K., they independently did experiments.
What did they do?
They fired beams of electrons at crystals, and they saw diffraction patterns.
Diffraction. That's classic wave behavior, like light through a grating.
Precisely. Electrons were behaving like waves, scattering off the crystal lattice in a way that only waves do. It was stunning proof.
So wave-particle duality wasn't just for light anymore, it was for matter, too.
It became a cornerstone of quantum mechanics. And de Broglie gave us the equation for it. Lambda equals h divided by p.
Lambda is the wavelength.
H is Planck's constant, that tiny fundamental number in quantum mechanics.
And p is momentum, mass times velocity, basically.
Right. So it directly connects a wave property, wavelength, to a particle property, momentum.
And it's an inverse relationship. More momentum means
shorter wavelength. The heavier something is, or the faster it's moving, the tinier its associated wavelength becomes.
That's going to be important later, I suspect.
Definitely. And de Broglie actually used this wave idea to explain something else that was puzzling physicists, Bohr's model of the atom.
Oh, yeah. Bohr said electrons could only orbit at specific energy levels, right? But he didn't fully explain why.
Exactly. It was more like a rule he imposed. De Broglie realized that if you think of the electron as a wave orbiting the nucleus, it has to form a standing wave.
Like a guitar string vibrating. It has to fit neatly.
Precisely. For the wave not to cancel itself out, the circumference of the orbit had to be a whole number of wavelengths, and that condition perfectly reproduced Bohr's allowed energy levels.
Wow, so the wave nature explained the quantized orbits. That's elegant.
It turned a postulate into a physical picture, a really powerful insight.
Now, there's a nuance here in how we interpret this matter wave, isn't there? De Broglie maybe thought of it as a real physical wave.
Initially, perhaps, but the modern view, largely thanks to Max Born, is different. The wave isn't a physical substance waving.
It's a probability wave.
Exactly. It's a wave of probability amplitude.
Yeah.
You square the amplitude of the wave at any point, and that tells you the probability of finding the particle right there if you were to measure it.
So it's about likelihood, not a physical ripple.
Correct. And this applies not just to fundamental particles like electrons, it rigorously applies to composite objects too.
Like a baseball.
Like a baseball. You can define a wave function for the baseball's center of mass, and it behaves quantum mechanically just like a single particle with the baseball's total mass and momentum.
So asking about a baseball's wavelengths isn't just like a fun thought experiment. It's actually meaningful in quantum mechanics.
It is mathematically meaningful, yes. Whether it's observable is another question entirely.
Okay, that leads perfectly into the next big question. If a baseball has a wavelength, why on earth don't we see it acting like a wave? Why doesn't my car diffract when I drive past a lamppost?
Right, this comes down to the sheer scale involved. The numbers are just staggering.
Let's look at some examples from the sources. An electron, say in an electron microscope, what's its wavelength?
It's tiny, but measurable. Around 7.3 times 10 to the minus 11 meters. Small enough to probe atomic structures, which is why electron microscopes work.
Okay, measurable. What about something bigger but still small, like a buckyball molecule, C60?
Even those have been shown to exhibit wave behavior in experiments. Their wavelength is about 8.8 times 10 to the minus 12 meters. Still incredibly small, but experimentally accessible with careful setups.
All right, now let's scale up. A grain of sand.
Okay, now it gets ridiculous. For a slowly moving grain of sand, the wavelength is something like 6.6 times 10 to the minus 28 meters.
10 to the minus 28, that's unimaginably small.
And it gets worse. A baseball thrown at, say, 90 miles per hour.
Uh-oh.
Its de Broglie wavelength is calculated to be around 1.1 times 10 to the minus 34 meters.
Okay, that number barely means anything. It's just tiny. What about my car?
Your mid-sized car driving along?
Yeah.
Roughly 1.5 times 10 to the minus 38 meters.
Minus 38. So what does this mean for seeing wave behavior?
It means it's completely impossible. Remember, to see wave effects like diffraction or interference, the wave needs to interact with something roughly the same size as its wavelength.
Like slits in a barrier or an obstacle.
Exactly. So to see a baseball diffract, you'd need slits spaced about 1034 meters apart.
And how small is that compared to, say, an atom?
An atom is vastly larger, around 10 meters. Even a proton is huge in comparison, about 10-15 meters.
So 1034 meters is smaller than anything we know.
It's smaller than the Planck length.
Ah, the Planck length. That's like the fundamental pixel size of the universe, right? About 1.6 times 1035 meters?
Kinda, yeah. It's generally considered the smallest meaningful length scale in physics. So the wavelength of a baseball is smaller than the smallest possible distance.
So there's literally nothing in the universe small enough to interact with it in a way that would reveal its waviness. The scale just makes it utterly insignificant.
That's a huge part of the story, yes. The sheer smallness of the wavelength for macroscopic objects is a major factor.
But you said part of the story. Is there more to it than just scale?
There is. It's not just that the wavelength is too small to see. There's an active physical process that destroys the quantum coherence needed for wave behavior in large objects. It's called quantum decoherence.
Decoherence. Okay, what's that about? You called it an active erasure earlier.
That's a good way to put it. Think about that baseball or your car. Is it ever truly isolated?
No, of course not. It's constantly bumping into air molecules, photons are hitting it, there's thermal radiation.
Exactly. Billions upon billions of interactions every fraction of a second. And each tiny interaction acts like a measurement.
A measurement? How so?
In quantum mechanics, to see wave interference, an object needs to be in a superposition of states like being in multiple places at once. In a probabilistic sense, that's coherence.
Okay.
But every time an air molecule bounces off the baseball, or a photon reflects from it, information about the baseball's position leaks out into the environment. The baseball's quantum state gets entangled with the states of all those air molecules and photons.
Entangled, meaning linked together.
Yeah. The delicate superposition of the baseball alone is destroyed. It gets mixed up with the environment. From the perspective of just the baseball, its coherence rapidly vanishes. It behaves classically.
So the environment is constantly watching or measuring macroscopic objects, forcing them out of quantum states?
That's the essence of it. And this process is incredibly fast and efficient for large objects because they interact so strongly with their surroundings. Even one interaction can be enough to collapse the wave function locally.
So even if we could build a baseball-sized double slit somehow, decoherence would kill any interference pattern before it could form.
Almost certainly, yes. The environment ensures macroscopic objects behave classically.
Are there any exceptions? Big things that do show quantum behavior?
Yes, but under very special conditions. Superconductivity and superfluidity are examples.
Where materials have zero electrical resistance or flow without friction at low temperatures.
Right. In those systems, vast numbers of particles act in a coherent quantum state. But it requires extremely low temperatures to minimize environmental interactions and specific types of particle interactions that maintain coherence.
So it proves size isn't the only factor. It's really about isolation from the environment, or lack thereof.
Precisely. It's the coupling to the environment and the resulting decoherence that is the dominant reason why the macroscopic world looks classical.
Okay, so the everyday world emerges because quantum effects are either too small to see or actively erased by decoherence. But what if there's something even deeper going on, beneath quantum mechanics itself?
Now you're opening the door to the really fundamental questions. And that's where string theory comes into the picture.
String theory, the leading candidate for that theory of everything. What's the basic idea?
At its heart, it's simple, almost deceptively so. It proposes that the fundamental constituents of reality aren't point-like particles,
Like electrons and quarks in the standard model.
but tiny one-dimensional vibrating filaments of energy, strings.
Like infinitesimally small guitar strings.
Kind of. And just like a guitar string can vibrate in different ways to produce different notes,
Harmonics, yeah.
these fundamental strings can vibrate in different modes. And each distinct vibrational mode corresponds to a different type of elementary particle.
So an electron is just one way a string is vibrating.
Yes. And a photon is another way it's vibrating, a quark, another. All the particles we know, and maybe others we haven't discovered, are just different notes played by these fundamental strings.
That's incredibly elegant. It potentially unifies all particles into one fundamental object.
That's the appeal. And properties like mass, charge, spin, they aren't inherent properties of points anymore. They're consequences of how the string is vibrating, its energy, its topology.
It comes with some pretty wild requirements, doesn't it? Like extra dimensions?
It does. For the mathematics of string theory to be consistent, it doesn't work in our familiar 3 spatial dimensions plus time. It requires extra spatial dimensions. Most consistent versions require a total of 10 space-time dimensions, 9 spatial dimensions plus time.
9 space dimensions. Where are the other 6?
The idea is that they are compactified, curled up into incredibly tiny, complex shapes at every point in our familiar 3-dimensional space. Way too small for us to perceive directly.
Like tiny rolled-up scrolls attached to every point.
Something like that, yes. And the precise geometry of these curled-up dimensions is actually crucial.
How so?
It influences the possible ways the strings can vibrate, which in turn determines the properties of the particles we see in our large dimensions, like their masses and charges.
So the shape of the hidden dimensions could explain why particles have the properties they do.
That's the hope. It's one of the most compelling aspects of the theory.
And there's another requirement, supersymmetry.
Yes, supersymmetry, or SUE-CY. This is a theoretical symmetry that relates the 2 fundamental classes of particles. Fermions, which make up matter like electrons and quarks.
And bosons, which carry forces like photons.
Supersymmetry predicts that every known particle should have a heavier superpartner particle with different spin properties. So, every fermion has a boson partner, and every boson has a fermion partner.
We haven't found any of these superpartners yet, though.
Not yet, no. That's one of the challenges. But mathematically, supersymmetry is very important for string theory. It helps cancel out problematic infinities that arise in the calculations and stabilizes the theory.
Okay, so strings, extra dimensions, supersymmetry. Where does this theory live? What's its natural scale?
It lives at the Planck scale.
Back to Planck. So the strings themselves are roughly Planck length, that 1035-meter scale.
Yes, that's thought to be their characteristic size. And the energies involved are Planck energies, around 1019 giga-electron volts.
Which is huge compared to our particle accelerators.
Quadrillions of times higher energy than the Large Hadron Collider can reach. This incredible energy scale is why we can't just make strings in a lab and study them directly. It's experimentally inaccessible.
So how can we possibly know if it's right? Is there any prediction it makes that's, well, testable, or at least remarkable?
There's one absolutely stunning prediction. When you analyze the vibration modes of a closed string loop,
A string loop.
one of its lowest energy vibrational modes corresponds exactly to a massless particle with spin 2.
And what does that signify?
That is precisely the expected property of the graviton, the hypothetical quantum particle that carries the gravitational force.
Wait, so gravity isn't something you have to add to string theory?
No,
Yeah.
it just emerges naturally from the theory itself. One of the vibrations of the string is the carrier of gravity.
That's huge, because combining gravity with quantum mechanics was the whole problem we started with.
Exactly. String theory doesn't just accommodate gravity, it requires it. This inherent unification of gravity with the other forces, which correspond to other string vibrations, is why it's considered the most promising framework for a quantum theory of gravity.
Okay, that is genuinely remarkable. So how does this stringy picture relate back to the de Broglie wave we talked about earlier? Is a particle's de Broglie wave just another string vibration?
That's a great question. and it highlights an important distinction. The string's vibration mode defines the particle's identity, what it is: an electron, a photon, a graviton.
Its intrinsic properties, like
Right.
mass and charge.
Right. The de Broglie wave, on the other hand, describes the quantum mechanical motion of that particle's center of mass as it travels through spacetime.
So vibration is what it is. De Broglie wave is how it moves and where it's likely to be found.
You've got it. There are different aspects of the particle's reality within the framework. String theory provides the what, quantum mechanics, describing the motion via the wave function, provides the how.
And you mentioned the shape of the extra dimensions affects the what.
Yes. The geometry of the compactified dimensions dictates the allowed vibration patterns, which in turn determines the spectrum of particle masses and charges we observe in our large dimensions. Potentially, it could explain the seemingly arbitrary values in the standard model.
Okay, so if string theory is potentially deeper than standard quantum mechanics, does it change quantum mechanics or build on it?
Traditionally, string theory is formulated using the principles of quantum mechanics. You quantize the string, applying QM rules to its vibrations and interactions.
So QM is still fundamental in that picture.
In the standard formulation, yes. However, string theory does predict subtle modifications to quantum mechanics at extremely high energies or small distances, near the Planck scale.
How so?
The most famous example is a modification to Heisenberg's uncertainty principle.
The one that says you can't perfectly know both position and momentum simultaneously.
Right. String theory suggests a generalized uncertainty principle, or GUP. It implies there's an absolute minimum length scale, the Planck length below which you simply cannot measure position, no matter how much energy you use.
Why not? In standard QM, more energy means a shorter wavelength probe, meaning better precision.
In string theory, if you try to probe space-time at distances smaller than the Planck length using a very high-energy collision, you don't see smaller details. Instead, the energy you pump in actually creates a larger disturbance. The probe string itself gets excited and grows larger, effectively blurring the measurement at that scale.
So the Planck length acts as a fundamental resolution limit for space-time itself.
That's the idea suggested by GUP. It prevents probing arbitrarily small distances.
That's fascinating. But then, could it be even more radical? Could the rules of quantum mechanics themselves emerge from string theory rather than being assumed?
Now you're touching on some really deep speculative research. There's work, for example, by physicists like Bars and Richkov, suggesting that the fundamental rules of QM, like the commutation relation between position and momentum, x, BAPAI, might not be postulates after all.
What would they be instead?
They might be derivable consequences of the underlying geometry and topology of how strings interact, how they join and split.
So the weirdness of quantum mechanics, the probabilities, the uncertainty, might actually stem from the behavior of these extended objects, these strings.
That's the tantalizing possibility. If true, it would mean quantum mechanics isn't the bottom layer, it's an emergent behavior of a deeper stringy reality.
Wow. And does this connect to other mind-bending ideas like the holographic principle?
Very much so. The holographic principle, particularly in the context of the AD-SCFT correspondence.
Okay, break that down slightly.
AD-SCFT is a powerful mathematical duality. It suggests a deep equivalence between a theory of gravity, like string theory, in a certain kind of curved spacetime called anti-de Sitter space, ADS,
Okay.
and a non-gravitational quantum field theory, CFT, living on the boundary of that spacetime in one fewer dimension.
So a theory with gravity in, say, 5 dimensions is somehow the same as a quantum theory without gravity in 4 dimensions.
Mathematically, yes. Like one is a hologram projected by the other. It stunningly suggests that gravity and maybe even spacetime itself might not be fundamental.
Space-time isn't fundamental.
Yeah. It could be an emergent phenomenon arising from the quantum entanglement of degrees of freedom in that lower dimensional boundary theory. The geometry of spacetime could be encoded in the quantum information on the boundary.
So the structure of our reality might be a projection from a simpler quantum system.
That's the profound implication. It ties back to the idea of QM perhaps emerging from strings, and spacetime emerging from QM. It's all interconnected in these theoretical frameworks.
My head is spinning slightly. Let's try and connect these threads back to, well, our baseball. We established its de Broglie wavelength is tiny and its quantum nature is wiped out by decoherence. What does string theory add to that picture, practically speaking?
Practically speaking, for the baseball, almost nothing directly.
Really, all that complexity and it doesn't affect a baseball.
Remember the generalized uncertainty principle, the GUP modification? We calculated the correction it would introduce to the uncertainty relation for a macroscopic object like a baseball.
Then the number was?
Utterly, utterly negligible. Something like a factor of 10 to the minus 64. It's completely insignificant at everyday scales.
So even if string theory is the correct underlying theory, standard quantum mechanics without any GUP corrections works perfectly fine for describing baseballs, cars, planets.
Absolutely perfectly. The deep physics of strings is completely washed out by the scale and by decoherence long before you get to macroscopic objects.
Okay. But string theory does offer maybe a different way to think about the baseball's place in the universe, like these brain ideas.
Yes, brain world scenarios offer a neat picture. If our universe is a three-brain, a three-dimensional surface embedded in that higher dimensional spacetime,
Like a sheet of paper in a 3D room.
kind of, then particles like electrons and quarks, which make up the baseball, could be the endpoints of open strings that are confined to move only on that brain.
So we and the baseball are stuck on the brain.
Pretty much. But gravity, mediated by closed string loops like the graviton, isn't necessarily confined. It can travel off the brain into the extra dimensions, the bulk.
And that could explain why gravity seems so much weaker than the other forces, like electromagnetism.
Exactly. Gravity's influence gets diluted because it spreads out into more dimensions while the other forces are concentrated on our brain. It's a potential explanation for the weakness of gravity.
So the baseball is a collection of string excitations stuck on our universal membrane, and its de Broglie wave still describes as probabilistic motion on that membrane.
That's a good way to visualize it within that framework, yes.
And one last speculative connection. Could string theory eventually explain why the de Broglie wave is a probability wave? That Born rule?
That's still very much at the frontier of research. People are exploring connections through things like the many-worlds interpretation of quantum mechanics or other theoretical ideas trying to derive probability from deeper principles.
But no definitive answer yet.
No, it remains one of the deep conceptual mysteries. But string theory, by potentially providing a more fundamental description, might hold the key to understanding the origin of quantum probability itself.
So, pulling it all together, we have this incredible hierarchy. Classical physics emerges from quantum mechanics via scale and decoherence.
And quantum mechanics itself, maybe even space-time, might emerge from the deeper dynamics of string theory.
And the de Broglie wavelength of our baseball is like a tiny, valid, but completely hidden echo of that quantum reality, rendered unobservable by the layers above it.
That's a great summary of the picture.
It's been an amazing journey through these ideas. But string theory isn't without its problems, is it? What are the big hurdles, and where are researchers looking next?
A major challenge is definitely the landscape problem.
The landscape.
String theory doesn't seem to predict a single unique universe. Instead, the equations allow for a colossal number of possible solutions, or vacua. Each vacuum corresponds to a different way. The extra dimensions can be curled up, leading to potentially different physical laws, different particle masses, different fundamental constants.
How many possible universes are we talking about?
The estimates are astronomical. Sometimes you hear numbers like 10 to the 500 or even vastly more, like 10 to the 272,000, an unimaginably huge landscape of possibilities.
That sounds problematic. If it predicts everything, does it predict anything specific about our universe?
That's the criticism. It makes it very hard to extract unique, testable predictions. How do we find our specific vacuum state within that enormous landscape?
Are people trying to narrow it down?
Yes. That's where efforts like the Swampland program come in. The idea is to find general principles that distinguish mathematically consistent string vacua that could describe a realistic quantum theory of gravity from those that are inconsistent to swampland. It's about finding constraints to cut down the possibilities.
So without direct evidence, which seems impossible, what about indirect tests? Where might we see hints of string theory?
There are a few avenues. Cosmological observations are one. Scientists look for tiny signatures of Planck scale physics, maybe related to GUP, imprinted on the cosmic microwave background radiation.
The afterglow of the Big Bang.
Right. Or perhaps in the details of gravitational waves detected from black hole mergers or other extreme events. These could carry subtle information about the nature of gravity at its most extreme.
Anything closer to home? Lab experiments.
Yes, high-precision tabletop experiments are pushing the boundaries. Things like incredibly sensitive optomechanical systems, tiny vibrating mirrors or membranes or atomic interferometers.
What are they looking for?
They're searching for minuscule deviations from the predictions of standard quantum mechanics or general relativity. If they found a deviation consistent with something like GUP, it wouldn't prove string theory, but it would be powerful evidence for new physics at the Planck scale, where string theory operates. They set increasingly tight limits on these kinds of effects.
Okay. And is string theory the only approach to quantum gravity people are pursuing?
Oh no, definitely not. While it's arguably the most developed and popular, there are important alternatives. The main rival is probably loop quantum gravity, or LQG.
Loop quantum gravity. How does that differ fundamentally from string theory?
They start from very different places. String theory starts with particles, as strings, and aims for unification, with gravity emerging as one aspect of string behavior.
Right, the graviton vibration.
LQG, on the other hand, tries to directly quantize spacetime itself, using the principles of general relativity and quantum mechanics. It doesn't necessarily aim to unify all forces from the start.
So what does space-time look like in LQG?
It's fundamentally discrete. Space isn't a smooth continuum, but rather a network of interconnected quantum loops, a spin network. Area and volume themselves become quantized, meaning they can only take on discrete values.
Like space is woven from quantum threads.
Exactly. It's also background independent, meaning it doesn't assume a pre-existing space-time stage for things to happen on. The quantum geometry of space-time itself evolves. String theory, in its usual formulations, often relies on a background space-time.
So different philosophies, different mathematical tools aiming for the same ultimate goal.
Precisely. It highlights that the path to quantum gravity is still very much under construction, with multiple promising, though challenging, directions.
It really does bring us back to that hierarchy, doesn't it? The classical world we see is built on the quantum world.
Which might be built on strings or loops or something else entirely.
And that baseball's wavelength, while real according to quantum theory, is just completely swamped by the physics of emergence and scale and decoherence. It's a ghost of the underlying reality.
A perfect illustration of how different layers of physical description operate and obscure one another. It's been quite a journey, from Planck into Broglie all the way to brains in the landscape.
Indeed. From that basic conflict between the big and the small, through matter waves, hidden dimensions, vibrating strings, emergent spacetime. It's mind-boggling stuff. So maybe a final thought to leave our listeners with. What if the solid, predictable, classical reality we take for granted? What if it isn't the fundamental state of affairs at all?
What if it's more like an illusion? A very stable, very persistent illusion.
It's carefully constructed by the universe's deepest, weirdest rules. Maybe our everyday world is just, I don't know, the lowest, most boring note in an incredibly complex, hidden, stringy symphony playing out at the Planck scale.
That's certainly a provocative thought to ponder. What reality looks like when you peel back the layers we can perceive?